Time for section 1.8, perimeter, circumference, and area. We need to go over a few things before we talk about perimeter and area. First, we need to go over what a polygon is. A polygon is an enclosed shape consisting of 3 or more line segments. You have worked with them for a while. Triangles are a polygon. Rectangles are a polygon. The definition I've given you is the shortened form of the full-length definition. The full-length one talks about the line segments needing to connect at the endpoints. So something like this doesn't count. This line segment here is not connecting at the endpoint. And you can't have 2 consecutive sides part of the same line. So something like this isn't allowed, where these 2 line segments just form one big line segment. Now, if you took those and combined them and made 1 line segment instead of 2, then it would be a polygon. In general, though, you won't need to spit out the official definition. You just have to have the basic idea of what a polygon is. With that basic idea in mind, which of these shapes count as a polygon? Let's take these one at a time. This top left one absolutely counts. This one is not enclosed, so it's no good. If you take this whole thing, that is not a polygon. However, if you split it up and took them individually, then we would have 2 individual polygons, 2 triangles. But as a whole shape, not a polygon. The lines are not allowed to cross. This one over here, that works. That is a polygon. This one here also works. That one is a polygon. And finally, this one over here does not count. It has a curved edge, and a polygon is made up of line segments, so that one does not count. Let's quickly go over some polygon anatomy. The line segments, which comprise a polygon, are known as the sides of the polygon. Each endpoint of a side is known as a vertex. If you have a bunch of them, like here, then you refer to them as vertices, or less commonly, as vertexes. This is the official definition of a diagonal of a polygon. Like many things I have said so far, the official definition isn't that helpful, and is overly complicated for a concept you probably could have guessed without me telling you. If the definition helps, great, but it is not necessary to memorize. Just get the basic idea. This polygon has no diagonals. This polygon has 2 diagonals. Here they are. This polygon has 5 diagonals. If you draw them all in, it makes a nice little star. This polygon has 20 diagonals. I suppose you'll want to see them all at this point, huh? Do you know how much animating that will be? Okay, fine. Here you go. Was it worth it? Glad I didn't choose a polygon with 12 sides. That would have been 54 diagonals. Overall, you probably have a good idea of what a diagonal of a polygon is. You don't need that definition. Now to convex versus concave polygons. The polygons we have been working with are all convex polygons. All of the polygons on this page are concave polygons. That is somewhat newer terminology, though. Older style terminology would have described those as non-convex, sometimes hyphenated, sometimes not. Either one is fine and correct. Use whichever term you like best. Which brings us to the next question. What is the difference between these convex and concave/non-convex polygons? Do you notice anything that the top group has in common compared to the bottom group? You can pause if you want to think about it a sec before I give you the answer. For the bottom group, I usually have students describe something to the effect that the polygon goes in on itself or something similar. The official definition is a little confusing, so there's a method that seems to work well for students, the rubber band test. For the convex polygons, if I were to stretch a rubber band, it would follow the edge of the polygon perfectly. However, for all of the concave polygons, if I were to stretch a rubber band around the edge of these polygons, at some point, at least once, the rubber band would jump a gap. It would no longer follow the edge of the polygon perfectly. For the lightning bolt, I have a couple gaps that it's going to jump. 2 on this side and 2 on this side. There are some common polygon names that you should know, and in many cases probably already know. A polygon with 3 sides is known as a triangle. A polygon with 4 sides is known as a quadrilateral. This quadrilateral is a square. This quadrilateral is a parallelogram. This quadrilateral is a rectangle. This quadrilateral is a trapezoid. Those are all specific names for specific types of quadrilaterals, and we will cover each of those special quadrilaterals later. But the term quadrilateral works for any of them. A polygon with 5 sides is known as a pentagon. A polygon with 6 sides is known as a hexagon. You will notice that we skipped 7. This section is covering common polygons, and sadly, the 7-sided polygon just doesn't come around very much. Which is good, since mathematically it isn't very nice either. Things don't come out very evenly. So the next common polygon is the octagon. And yes, that bottom one is a concave polygon instead of convex, but it is still an octagon. Of course, the most common octagon people are aware of is the stop sign. And in Charleston Park in Vancouver, Canada, they apparently really want you to stop. I wish it was just a real quirk of government gone silly, but these signs are actually part of an art installation for a biannual public art exhibition. Do you think it is nice art? Yes, we are skipping 9. Just like 7-sided polygons, 9-sided polygons are pretty rare. So we move on to 10. And a 10-sided polygon is known as a decagon. So those are all the names you really need to know. They come up quite a bit, and we'll be using all of them in this class. Now we have some which aren't so common. You don't need to memorize the names of these, but you may find them interesting. First up, the heptagon. That uses the Greek root and is the more common term, but if you want to use the Latin root instead, it would be a septagon. Nonagon, 9 sides. Hendecagon, 11 sides. Dodecagon, 12 sides. I almost consider dodecagon for the common list. It comes up every once in a while, but that's it. So you should at least be aware of the dodecagon and be exposed to it. But the rest of them on this list are hardly ever seen at all. Chiligon is such a good name. After seeing this, a lot of students will remember megagon since it's a cool name and concept. The last one is really theoretical rather than practical. Actually, megagon is almost theoretical too. It has been used as an example of something that is precisely defined but cannot really be visualized. A megagon would have to be unimaginably large for it not to look like a circle. But then you would have to be so far from it to see it all that it would still look like a circle. Now, I've told you the names that you really need to know. Triangle, quadrilateral, pentagon, hexagon, octagon, decagon, maybe dodecagon. But we need a way to talk about the rest of them. There are Greek and or Latin roots for every conceivable combination of number. But memorizing all of those would be for a Greek or Latin class, not math class. Mathematicians need something a little easier to work with, so they came up with the n-gon notation. With the n-gon notation, you simply replace the n with the number of sides you have. Instead of heptagon, you can say 7-gon. Have 43 sides? 43-gon. 21,547 sides? That's a 21,547-gon. The last one is kind of ridiculous, but it gets the point across. N-gon notation is really easy to use. Just plug in the number you need. When you want to name a polygon, we need to have the vertices labeled. So let's do that now. With those letters in place, we first state the name of the shape we are working with. In this case, that's a pentagon. Then choose one vertex on your shape. It doesn't have to be alphabetically first. I'll choose C. With that point chosen, now go clockwise or counterclockwise around your polygon until you have named all of the vertices. I will go counterclockwise. If I go counterclockwise from C, I'm going to end up with pentagon C, B, A, E, D. That obviously isn't the only possibility. You could have done pentagon A, B, C, D, E, pentagon D, E, A, B, C, pentagon B, C, D, E, A. Doesn't really matter. Choose a vertex, choose clockwise or counterclockwise, and then just name them all in that order. With that background information done, we can get to the main part of this section, which hopefully is still review for you. First, we have perimeter. Perimeter is simply the distance around an object. It has nothing to do with the inside of the object. Perimeter is a calculation of length, and thus it is a linear measurement. I have a lovely pentagon below. Calculating perimeter would be like taking my pentagon apart like this and straightening it out. You can see that this pentagon is going to be laid out in a line, and the perimeter is just the length of that line. Or you can think of it another way. Here I have a lovely little ant. He's out for a little stroll. He comes across a pentagon drawn in chalk on the ground. Perimeter measures how far the ant would need to walk in order to make it around the whole pentagon. As I have shown in the previous two examples, perimeter is a calculation of length. It's a linear calculation. Because of that, perimeter is always measured in just units, not units squared, like 8 inches, 9 centimeters, 4 millimeters, or whatever. Getting your units right might seem like a tiny detail, but that tiny detail can mean remarkably different things, so be careful to get your units right. There will be a lot of formulas as we move through the year, but let's start off with some of the easy ones. If each side of a square is of length s, then the perimeter of the square is of length 4s. Before I move on to the rectangles formula, a word about labeling. In many grade schools, they label the sides of a rectangle as length and width, like I have shown here. However, now that you have hit geometry, it is time you make the switch to what we will be using most of the time in geometry class and beyond. You need to get used to seeing base and height instead of length and width. It's a small change, and many of you probably have already switched, but it is something I am mentioning now to get everyone on the same page before going on to the formula. The perimeter of a rectangle is 2 times the base plus 2 times the height. The triangle formula is kind of brute force. You just have to go old school and add up all the sides. That isn't much of a formula, but that's what you do. And then we get to the perimeter of a circle, which is known as circumference. Why does it have a new name? Why can't we just say the perimeter of a circle? Why did Circle get a special name for himself? Is he super important? Why does he get a special name for his perimeter? Who does Circle think he is? I don't really know why the circle has a special name for its perimeter, but that's the case, so we will never talk about the circle's perimeter. We will always talk about its circumference instead, but they are the same thing. The formula for a circle's perimeter, its circumference is 2 pi r, or pi times the diameter. Either one is fine. Use whatever one works for you. Now we get to area. Perimeter measures the distance around an object. Area measures how much stuff is inside of an object. Consider this hexagon below. Let's assume it is a piece of denim, which has been cut to that bizarre shape. Area is calculating how much denim material is used in that shape. Area is not a linear measurement like perimeter. It is a different calculation. But what exactly are we measuring? I have a lovely rectangle below. Let's chop them up. My dissection job has left this rectangle chopped up into perfect little squares that are 1 centimeter on a side. This means that each little square is 1 centimeter squared. As a bonus fact, that's why the little exponent to the second power is pronounced as squared. You have probably said some variable is squared when raised to the second power a lot, but how many of you knew why it was pronounced that way instead of to the second power? In any case, area is a calculation of how many little squares make up the inside of a shape. You are literally counting up squares, or parts of squares. Because of that, your units for area calculations are always units squared, whether 8 centimeters squared, 7 yards squared, 12 miles squared, or whatever. Now we get to the area formulas. First, the square has an area of sides squared. The rectangle's area is base times height. Note that a square is also a rectangle, so you can use base times height on a square, too. The area of a triangle is 1/2 the base times the height. Let's assume my base is down here. Normally this is pretty straightforward, but if people make a mistake, it's because of this. Make sure you are using the correct height. A circle's area is pi r squared. Lastly, we get to the area addition postulate. It helps in situations like this Tetris piece. What is the area of this Tetris piece? What formula should we use? Is there a formula for Tetris pieces? No. That's why we need the area addition postulate. The area addition postulate says that the area of a region is the sum of its non-overlapping parts. Basically, it says that when you encounter an odd-looking shape like this, chop it up into pieces that you can find. By cutting the piece here, I have made 2 rectangles. There is definitely a formula for a rectangle, so we find the area of each individual rectangle and add them together to get the area of our Tetris piece. Note that this is not the only way we could have chopped this piece up. I could have also done this. This also makes 2 rectangles, or actually 1 rectangle and 1 square. Either way, I could find the area of them individually and then add them together to find the area of my original piece. There are many ways you could have chopped this thing up. Use whichever way you like best.